Welcome to Diplomatic Derivatives. Today we're going to jump on to the next topic in our series of lectures about the group theory, where in the first video we talked about the group theory itself, what a group is, and what are the four rules that are required for some set to be called a group. So you've got the hang of what a group is. What if we just take a piece of that group and it still behaves like a group on its own? That's what we call a subgroup, and today we're going to break it down into simple language, super simple, no jargon overload. In a simple manner, what we say is, first of all, we have a group. This is a very basic notation for a group, that is G. And subgroup, in simple words, is a smaller group inside a bigger group. Its definition, we see what is a subgroup. A subgroup is just a smaller group that lives inside a bigger group, and it follows the same rules. So if we talk about the rules, we've seen that there are four rules that are supposed to be followed for a set to be called a group. That was namely closure, associativity, identity, and inverse. Subgroup follows similar rules. So formally, if G is a group, a subset H subset of G is called a subgroup. So whenever we write a set, right, and we make a smaller set which is a part of the bigger set, we basically say it's the subset of the bigger set, right? So H is a set, it's a small set which is the subset of a bigger set G, and this H will be called a subgroup if the conditions now. H is non-empty. So first condition is H has to be non-empty. There has to be an element in H. The operation from G works the same way in H. So whatever operation we have on G, for example, when we talked about in the previous lecture, we said that we have a set, let's suppose Z, and the operation is addition. So addition is going to be an operation which is going to be performed on the set, and then we'll prove with the help of the rules whether that operation is true for that particular set or not. If it's true, then that set is a group. In a similar way, the operation which works on G must work on H as well. H is a group on its own. So H itself follows all the four rules that G follows. So if these conditions are true, therefore H is also a subgroup. So H is a subset of G, and these conditions are fulfilled, therefore H is a subgroup. So now what we're going to do is we're going to prove how H is a subgroup. Okay, we're actually going to perform it. So first of all, we have this term which is the subgroup test. This test is performed on any set in order to prove if it's a subgroup or not. So let H is a subset of G. Then H is a subgroup if, so we know that H is a subset, right? But we have to prove if it's a subgroup. Subset means all the elements of H are in G, and H is the smaller set. So we know that H is the subset. Whether or not H is a subgroup, this is how we're going to prove it. So what we do is we take three conditions. First one being the closure property, that for all AB element of H, the result A star B is also in H. Simple, like how we did for the group. Identity, the identity element of G is in H. So whatever is the identity element of G, that element has to be present in H as well. That's point number two. Third is for all A element of H, the inverse A inverse is also in H. So that's similar to the previous lecture, that for any element there is an inverse of that element which is also present in H, such that A dot A inverse is equal to E, which is the identity element. Okay, we will take this with the help of an example. So we have example for integers and even integers. So we have two sets. We have the sets of integer and we have a set of even integers. Okay, the bigger group, the set of integers, of course, that is Z, and the operation on it is addition. The smaller group we have is a small set which is even numbers. So it's going to be 0, 2, 4. We remove all the odd numbers. That we don't remove the negative numbers because it's not Z to the power plus, it is Z only, right? So it's only even integers. It's not only positive even integers. If it's only positive even integers, then we will have only 0, 2, 4 and so on. But it's only even integers, so we have 0, 2, 4, 6 and so on, and on the negative side as well, -2, -4 and so on, right? So we have the bigger group here, and this is the smaller group. So we can clearly see that this set is the subset of the bigger set, right? Now you have to prove whether it's a subgroup or not. So we will take the three rules. First one, we have closure. Yes, it is closed because any even number plus even number will give us another even number. So if we take 2 plus 4, we get 6. Similarly, -2 minus 4, we get -6. So it's still part of the system, okay? Identity, 0 is in there. So we have 0. And even for this bigger group, the identity element is 0. And that 0 is present in the smaller set, right? So identity is present. Inverses, negative of an even number is still even. So 2, the additive, and since it's addition, the operation over here is addition, we take 2 and we have to get the identity element 0. So 2 added with -2 will give us 0. So the inverse of this element exists within the set, right? Therefore, three properties are proven. Therefore, we can say that this small set is also a group. Okay, so that's how we will check whether a smaller set is first of all, the smaller set is a subset of the bigger set, and then we prove if it's a subgroup. So we'll take the three properties, we'll prove the properties, and once we're done, we will understand whether it's a group or not. Okay, now there is a shortcut tip over here, and that tip is, if you're dealing with a group under addition, you only need to check, is it non-empty and is it closed under subtraction? If yes, it's a subgroup. So what does this mean? In the previous slide, we saw that there were three things. The first one was the set H has to be non-empty. That is, there has to be an element within the set, right? So the tip over here is, if we are talking about any set which is going to be performed under the operation of addition, particularly, okay? So we are talking about only one operation, which is addition. So if you get a question which is about the set under addition, right, and we have to check whether it's a subgroup or not, first we check whether it's non-empty. It's non-empty, there is an element inside it, okay, correct. Then we check if it's closed under subtraction. So we just check the closure property. Okay, we take two elements from the set and then we are going to subtract them, and if we get the answer within the set itself, therefore it's closed under subtraction. If these two properties are fine, it is a subgroup. It is a subgroup. There, you don't have to go to the next two properties. If these two things are checked, therefore the set given to us is a subgroup. Move forward to another part of the video, which is about why do subgroups matter. Now, actually, there has to be a reason why we are studying about the entire group theory, right? And that we dealt in the previous lecture when we said that it's all about structure and symmetry all around us. We see there is a pattern that things follow, how different puzzles are solved, how different machines work, and that's why also, for a similar reason, subgroups matter. Now think of it as a complex machine, lots of moving parts. Okay, we see a lot of moving parts in this machine. Okay, all working together according to certain rules. So there are certain rules, either they will go clockwise or they'll go anti-clockwise. Okay, now when we zoom into a particular part, so there are different parts. If we zoom into a single part over here, it's smaller for sure, but it follows the exact same rules as the whole machine. It moves in sync. So if this moves in this direction, this particular element is forcing the bigger thing to move in a particular direction, right? So there is a pattern at play. It's structured, and when you study how this one works, this one particular piece works, you get the real insight into how the entire system works. Okay, so if you study one part, you will understand how the rest of the machine is working. That's the power of subgroups. So They basically have the power to simplify the bigger picture. They help us understand the group's structure, break it down into smaller parts, and explore symmetry and pattern at a deeper level. Okay, so when we talk about the Rubik's Cube, or when we talk about different kinds of puzzles, we talk about machines, we see there is a pattern at play, and subgroups are something that allows us to understand it at a deeper level. Okay, all without losing the logic of the original group. So you have something original, that's a bigger group, and it has a logic. That logic remains intact. Okay, and that follows into the smaller ones. If you understand the smaller piece, you can understand the bigger piece. Okay, that's why the subgroups matter. So in this video, we talked about subgroups as we try to understand what subgroups are, that they're just groups hiding inside other groups, following the same rules just on a smaller scale. If that clicked for you, drop a like and hit subscribe for more maths. Next up, we're looking at an example in close-up to begin with actually solving theorems in group theory. Thanks for watching and see you in the next one.